Okay, so this is lecture number 3. This is about measuring mass. Mass is another quantity in this class that we will use a lot when we do lab investigation. So how can we define it? Mass basically measures how much stuff something contains. Okay, so think of how many particles something contains. What are some tools that we can use? Think back to our equipment lectures. You can use a digital triple beam or a double pan balance. Digital is what we'll primarily use in here. It's pretty easy to use, and we're going to have to go through the steps of how we use that, okay? So SI unit for mass is a kilogram. Notice there is a prefix, okay? Kilo means 1,000, so the SI unit for mass is basically 1,000 grams. We're basing everything off of 1,000 grams, okay? Well, what can we say? One paperclip is about the equivalent as to 1 gram. Okay, one paperclip is roughly the mass of 1 gram. So here we go. Okay. How can we compare the two systems with mass? So the metric system and the English system, we're always going to compare these. 1 kilogram, so 1,000 grams. I apologize. So 1,000 kilograms is roughly 1 ton. Let's think of this and try to make sense. 1 ton is around 2,000 pounds. There are some different television shows, and they talk about tons for amounts of rocks that they haul or gold or things like that. Well, what is 1 pound? 1 pound is roughly equal to 16 ounces, okay? And we measure our weight, that we like to generically call it our weight, or our masses in pounds and ounces, okay? So let's go ahead and let's take a look at how we use a digital balance. Okay, when we use a digital balance, we have to pay close attention, make sure, number one, that it's plugged in, but we have to go through a process called zeroing the balance. When we zero a balance, this basically means that anything, any little dust particle or anything that is on the pan, it's not going to account for its mass separately. It's going to say whatever's on there is on there, and its initial mass is 0, okay? So how do we do that? You hit the button on the scale that says tare, or so it's T-A-R-E or 0, and that's going to get us to a 00 reading, okay? We want to add whatever the solid object is to that balance. So like a cube or a paper clip, a lump, a rock, whatever. We want to add those to the balance, and then we will record the mass, okay? Recording mass is simple. You just mark it down on your data table, but there are some things that we need to pay attention to. What if whatever we're trying to find the mass of is a liquid or a powder? We obviously can't pour those directly on the pan of the balance, so we have to do a couple different steps. First, we want to take the mass or find the mass of any container that you're going to utilize to hold an object, okay? So you want to find the mass of the container with those above steps that we just talked about. Zero the balance, record the mass, okay? We're going to call this our initial mass, okay? Then we're going to add the irregular substance to this container that we already know the mass of, okay? We'll record the mass again. That's going to give us a final mass. Well, here we have the mass of the container plus the substance, okay? But we just want to know the mass of the substance. Up here, this is the mass of just the container, okay? Well, how do we figure out what the mass of just the substance is? The final, which is this, minus the initial. So it's the container plus the substance minus the container. That gives us just the mass of the substance. Pretty easy to do. We will do it quite a few times in this class so that we get used to it. Let's talk about mass versus weight. And this is something, again, where people try to interchange those terms. Mass versus weight, okay? Weight changes, so delta means changes. Weight changes based on the location of the object, thing, whether it's close to the surface of the earth, if it's on a different planet, whatever it may be, okay? Mass is always going to stay the same. I always like the mantra of mass stays the same, weight changes, mass stays the same, weight changes. The mass of an object will stay the same here on Earth. It will have the same mass on the moon, on Jupiter, Pluto, wherever it may be, okay? A lot of kids like to say, well, my mass changes. Well, yeah, if you eat a ton, just like I said in class, if I eat 40 donuts a day for 40 days, is my mass, or my quote-unquote, what we like to generically call my weight, is it going to change? Yeah, it's going to go up, okay? But the mass of an object, and this is saying if I have an object and I'm going to try to figure out the mass and the weight of the object in Colorado, Denver, Colorado, or here in Steubenville, Ohio, I will be able to figure out what the difference is based on the amount of gravity that comes into play. So let's take a look at what we have here. Here are 4 pictures of the same person, so this is the same stick figure. And this stick figure is on Earth, on the moon, on Jupiter, and on the sun. Okay, the mass of the person, you'll notice in each situation, is the same. It's the same person. Okay, but notice how the weight of the person changes. On Earth, 623 newtons. On the moon, 103 newtons. On Jupiter, 1,582 newtons. On the sun, 1,741 newtons. Okay? The person is going to have a smaller weight on the moon as they would the sun, because the value for gravity on the moon is way less here than it is here. Okay, so weight is basically dependent on the pull of gravity. If you take a look at these arrows that I put on here, this is more of a physics concept, but this is like a force arrow, and weight is a measurement in newtons, and that is a force vector. So we can use arrows to describe them. The larger the arrow, the more force or the more weight that is acting on an object. Okay, so mass stays the same, weight changes. So let's think about some things. Let's think back to what we've learned so far about mass, okay? Let's pretend I have 50 grams of feathers and I have 50 grams of bricks. Well, which of those would have a greater mass? You should be saying neither of them. They have the same mass, right? 50 grams of feathers, 50 grams of bricks, okay? Which of those would have a greater weight? Well, I know we like to say mass stays the same, but weight changes. But if they're in the same place, if both of these objects, the feathers and the bricks, are both here on Earth, they're going to have the same exact weight because they have the same mass. If we take feathers and put them on the moon and leave bricks on Earth, they will definitely have a different weight. Okay? Which of these objects would hurt more? If someone hit you with a bag of 50 grams of feathers and a bag of 50 grams of bricks, which one would hurt more? Okay. Hopefully you're saying the 50 grams of bricks, but can you support your answer as to why? Okay, so think about it for a second. Hopefully you're saying the bricks will hurt more because they're hard, the feathers are soft, okay? And some people try to fight that opinion, and that's okay. All right? Let's think back to volume, okay? We've talked about mass just now, and we've also talked about volume previously. Here I have 2 objects on a balance, okay? So here's my fulcrum point. This is my balance. These are my pans, okay? Notice by the picture, they're different sizes, or they have different volumes. But the objects have the same mass, okay? They have the same mass, but they have different volumes, okay? Objects can have the same mass, but be different sizes, okay? And when they're different sizes, those particles are just more spread out, okay? If you have any questions about that lecture, please make sure you do mark them down.